Section 3.3, subtraction of whole numbers. We're going to take a look at sort of the other half of what we just did in section 3.2 with addition. A lot of the pieces are going to look and feel very familiar, and there are going to be some new things along the way as well. To start with, we're going to take a look at what the definition for subtraction is. Subtraction of whole numbers says that for any whole numbers a and b, as long as a is greater than or equal to b, then a minus b will be the unique whole number c, such that b plus c is equal to a. And you know this to be true. If we were to take 6 minus 3, for example, we know that this equals, actually let me use 2 so that's distinctly different. 6 minus 2 is equal to 4. We know that this is true because 6 is equal to 4 plus 2. And that's exactly what this statement here is saying, is that it's sort of the missing piece. There are three models, for subtraction that we're going to take a look at. The first model is the one we tend to go to when we talk about subtraction. In fact, if you ask a small child what subtraction is, they're very likely to tell you it's takeaway. And so here's an example of the takeaway model for subtraction. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? Right, so you have something and somebody takes a portion of it away. And maybe it's because, it's an object that's actually stolen, lost, eaten, who knows, but it's removed from what you currently have. So if we're taking a look at solving this, we can actually do this. One way to do this would be with a concrete model. And so we can talk about having physical objects, right? These are my rocks. By definition, these are my rocks. Yes, I know they're blue, but we'll be all okay with that. So I have 6 here. I'm going to just copy and paste some here. So here's pasted. There's 6 more. That makes 18. And there's my 24. So I have my 24 rocks. And as the description is, we actually have a little brother sneaking into a room. He takes 5 of them away. So we're removing those 5. And if we count up what we have left, we have 19 rocks. A second model for subtraction is called missing add-ins. So this is the idea that we need something. We need a certain number of objects. We simply don't have all of them. It's not the idea that we had them and then we lost them or they were taken away, but we need them and we simply don't have all of what we need. So Lalisa needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lalisa need? So we're going to draw our current 8 leaves. Oops. Okay, so here's 4 leaves, 6 leaves, and 8 leaves. So this is what I currently have. And what I need is the missing part, and that's the answer to my question, right? I need to make 10 of these total. So in some sense, one way to do that is to draw this. I'm going to draw this in sort of dotted, right? They're needed. They're not really there. They're missing. So this is 10 total, and the portion that I have already is 8. Right, so my answer right here would be 2 leaves. And in terms of an algebra, sort of a statement or an equation, this is equivalent to saying 8 plus blank is equal to 10. The third model is a number line or measurement model. Now notice on both the first two, the takeaway model and the missing add-ins model, we're working with things that are typically sets. Right, I have objects that I count. I'm not talking about that they have size or dimension, but with the measurement or the number line model, we're talking about something that can be subdivided. In this case, we're looking at miles. We saw another example that was similar to this at the very first example, the very first lesson of these. It was doing things with feet, right? Lengths of, I think it was building material or something like that. So we've got Akeem, and he drives 15 miles to the mall. He's on his way home and his mom calls him to ask where he is. He states he's coming home and he's driven 8 miles so far. How far is Akeem from home? So we're going to draw a number line to represent this. And on our number line, we're starting at home, if you will. So I'll just draw a little house in here, right? Why not? We can draw a house. So here's home. And he's, going to the mall. The mall's big, so we're just going to draw it, big. And I'll erase this piece right there. So here's the mall, and the mall has You know, lots of roof lines. So there's my mall. Kind of looks like a castle, but we're going to pretend it's not. So this is the mall. And they're 15 miles between. So getting all the way from here to here is 15 miles. And we have Akeem. And Akeem says that he is 8 miles on his way back. So he's come back 8 miles, right? And the question is, how far does he have to go? So in some sense, we're sort of asking ourselves this length right here. So obviously my picture's not drawn to scale since the length looks bigger than the 8 miles I already drew. But that's okay, we can pretend. And our answer then will be that we have 7 miles more to go, or we're 7 miles away from home. So what I would do if I were in class with you right now is that I would have you take a moment and actually create 3 models. I'm having you do this in groups. Obviously, we're not in class today to do this. So I'd like for you to just pause the video and take a moment and to write 3 different word problems. 1 word problem that models taking something away. 1 word problem that models needing something and not having quite all of it. That's the missing add-end model. And 1 word problem that does something with measurement. So you're measuring things in feet, in miles, in ounces, whatever it is you're wanting to measure within something with measurement and subtraction. And then once you're done with that, go ahead and hit resume and we'll move on to the next part of the lesson. All right, the next thing we're going to take a look at is the idea of whole number properties for subtraction specifically instead of for addition. We'd encountered all 4 of these with addition and saw that they worked, and our question for us is whether or not these things hold for subtraction. In other words, is there a closure property for subtraction? Is subtraction commutative? And so forth. So the first one says closure. So the answer is that there is not a closure property for subtraction and for whole numbers. And what I want to show you is why that's the case. So with whole numbers and subtraction, if I were to subtract, for example, 3 minus 7, I would get -4. But -4 is not an element of the whole numbers, right? It's not a whole number. It's an integer, but it's not a whole number. So if we were actually looking at the whole number properties for, the integer properties for subtraction, we'd be good. Closure would work, but we're not. We're looking at whole numbers. So commutative. The commutative property does not hold either, and for example, we can actually take the same numbers we just had above, right? 7 minus 3, that's 4, and that works, but the problem is that this does not equal 3 minus 7. So commutative property, like switching the order of subtraction, doesn't hold. The associative property, unfortunately, doesn't hold either. And again, as an example, we will create one that shows this. If I do 3 minus 2 and then minus 1, I would actually end up getting, so 3 minus 2 would be 1 minus 1, so this would be 0. But if I, sort of checked this on the opposite side in the other order, if I did 3 minus and then I did 2 minus 1, well, this would be 3 minus and 2 minus 1 is 1, so 3 minus 1 would be 2. So these, of course, do not equal, so the associative property does not hold. And this is a counterexample to trying to think that it maybe does. And the last one is the additive identity property or the identity property. There is no subtractive identity property. And the reason is because of the commutative issues, right? So if I do 7 minus 0, you might feel like, hey, look, 0 is acting like an identity, right? 0 doesn't change the value of the 7. And this, in fact, does equal 7. The problem is if you go in the opposite order, you get -7. And these two things are not equal. And in particular, they don't both equal 7. All right, so we're going to shift our focus now to some models for subtraction. They're going to look very similar to the models we had for addition. The first one's called the concrete model. So the concrete model is the idea we talked about getting like Legos in a classroom, right, and actually snapping them together and unsnapping them and working it from that perspective. So in this one, we would have the same 34 that we had in our last lesson. So here's 34. But instead of adding on 18, I want to take away 18. So taking away 18, of course, means taking away 1 long, right? And then taking away 8 units. And the problem, of course, is that there aren't 8 units to take away. I only have 4 units. So what I do is I'm going to change my picture up a little bit. Instead of having 34 written as 3 longs and 4 units, I'm going to take one of my longs and change it into 10 units. Pardon the fact that my perspective is a little bit off, but you can imagine me doing that with the actual Legos, and they would all be the same size, of course. So once I've changed to sort of exchanged one of my longs into 10 units, I'm actually able to take away one long, right, and 8 units. So I can take away these 4, and I'll take away the top 4. And once I take those pieces away, what I'm left with is one long and 6 units. So my answer then is 16. And of course, even better if you're actually using the Legos and you can take them apart and, actually see the pieces disappearing as you take them away. Let's remind ourselves what the standard algorithm looks like. It's one you know and love, you're very familiar with. You start on the right-hand column and you're wanting to do 4 minus 8, which of course you can't, right? So there's not enough to take it away. So what we did is we called it borrowing back in the time that I learned it, and I suspect probably for you as well. The language that's used these days is actually regrouping. So we're taking the 3 and we're regrouping it to have 2 10s instead. And we're borrowing one of those 10s. We're regrouping one of those 10s to be 10 ones. So I have 10 ones and I have 4 ones, so it makes 14 ones. So I would do 14 minus the 8, which would give me 6, and then 2 minus 1, which would give me 1. And so I'd get 16 by either borrowing or regrouping. It's a little clearer if I actually sort of do the in-between of the concrete model and the standard algorithm. It's called the expanded algorithm, and we did this before as well, where we take the 34 and we break it apart into 3 plus 4. And we take the 18 and we break it apart into 10 plus 8. But we're subtracting, so we're subtracting off the 10 and subtracting off the 8. The problem still remains that I can't do 4 minus 10. I'm sorry, 4 minus 8 because the 4 is smaller than the 8. So instead, I take 30 and I make it a 20. And those 10 add to the 4, so it makes it a 14. So you can still really see that the 20 and the 14 make the 34 to begin with, and then you can do your subtraction. So you end up with a 6 here. And it's, of course, positive because that's what I'm working with, right? And then I've got a 10 here, so I have 16 with the expanded algorithm. The last algorithm, do you remember when we did addition, we had one that was called opposite change algorithm? So whatever we did to one number, we had to do the opposite to the other number. This is the equivalency of that in subtraction. It's called the equal additions algorithm. So in this algorithm, again, the whole goal is to get there to be zeros. And in particular, I want the zeros on the bottom number because I'm, subtracting zeros is very nice. Whereas adding zeros, when I did that, it didn't matter whether the top or the bottom was 0. So here I really do want the bottom number to become 0 so that I don't have to do any borrowing. So when I add the 2 here, since I'm working, this is not opposite change, right? I've got to add 2 to the other number as well. So this is equal additions. I'm adding equal values each time. So now I have 836 and I have minus 160. The problem, of course, here is that I still would need to borrow in the tens place, right? 6 can't be taken away from 3. So I'm not quite done. I mean, if it could be subtracted right there, right, when we would, but I'm not done. So I need to equally add again, and then our goal is to make it a 0, so we add 40 to this, and we add 40 to the top value as well. And if you can imagine the way this works, so if I were standing up in the classroom and I had, let's go with Kylie standing right next to me. So Kylie is a student in another class of mine, and she's a little shorter than I am. And so we have a difference in our heights between the two of us. But if we were to both put on sort of 3-inch heels, right, then the difference in our heights would remain the same. We would be still the same distance apart in heights. That's the idea of what's happening here. The difference is still the same. So this gives me 876. Now it's minus 200, and I can do all the subtracting with no borrowing because I've got zeros on the bottom. So this is 76 on the bottom, and I have 6. So the difference here, the subtracted difference, is actually 676. Okay, and then again, also just like with addition, we're going to take a look at doing some subtraction in other bases. again, to put us kind of in our position as our students where we're a little bit uncomfortable with the base system itself that we're working in. So we're going to do that base 8 and base 3 just like we did in the last lesson. So base 8 has the digits 0 to 7, and then base 3 has the digits 0 to 2. So I'm going to show this in a couple of ways. I'm going to show you the standard algorithm, and then I'm going to show you one of the other algorithms just to give you some perspective of how it looks using different methods. So we're working inside of base 8, and I need to take 7 away from 4. And of course, it doesn't work, right? 7 is bigger than 4. So we're going to regroup. We're going to take one of our 8s, which is in the column with the 3 that I just marked out, and we're going to take one away to make it a 2. But when we borrow in base 8, we borrow 8, right? It's like me taking a long, and a long is 8 long, and I break apart the 8 that's long, and I add it to the 4 I already have. So 8 and 4 means I have 12 units. And so that if I have 12 units and I take away 7, I get 5. If I have 2 longs and I take away 1, I get 1. So this is 1, 5, base 8. And that's what the standard algorithm would look like. I'm going to show you equal additions algorithm. It's a very nice one actually for this, or at least for this particular problem. So again, the goal with equal additions is that I end up with some zeros on the bottom, making the subtraction not require borrowing. So if I have 1, 7 here and I were to add 1 to it, that would very nicely become 2, 0 in base 8. But if I add 1 on the bottom, I have to add 1 on the top with subtraction. So 34 plus 1 would actually be, 34 plus 1 would actually be 3, 5. And then I can subtract to give me 1, 5, base 8. Now I actually think, at least on this one, equal additions is a very nice approach, works very cleanly. All right, let's take again another look. We'll do one in base 3. So I have 1, 0, 0, 2, minus 1, 1, 0. And as you look at this one, what you might notice right off the bat is that the 2 minus 0s, we're good to go, right? I mean, the 1's column, good to go. But then when we get to the second column and third column and the fourth column from the left, or to the left, yeah, it's not so good. So I have to go all the way over here before I can borrow, and I borrow a 2, right, because we're working in base 2, so this becomes 0. And I borrow a 2, which is great because I can now do the 2 minus 1, but I still have the, this column right here that I can't subtract in, so I need to adjust that. So this 2 actually needs to be changed as well. So I'll have to borrow from the 2 to make it a 1, and I'll borrow 2 because I'm working in base 2. And then I can subtract. So in the 2's column, right, the second column from the right, I have 2 minus 1 would be 1. And then I have 1 minus 1, which would be, I'm sorry, I'm not in base 2. I totally forgot for a moment. I'm not in base 2, I'm in base 3. Let me adjust those. All right, let's fix. I am so sorry. All right, in base 3. Got carried away. So in base 3, this is a 3. I borrowed 3. And then I need to adjust by taking the 3 and making it 2, because I'm going to borrow 1, regroup. And again, I'm in base 3, so I borrow 3. Much better, much better. There we go. And of course, this is not right down here at the bottom either. Sorry about that. We're actually able to subtract now, so I have 3 minus 1 in the 3's column, which would give me a 2. And then I have 2 minus 1, which would give me a 1. So I have 1, 2, 2, base 3. Here we go. All right, and then we're going to do equal additions just, for fun, so you can see how that would look again. So I have 1, 0, 0, 2, and I have 1, 1, 0. And of course, I already have one of the zeros on the bottom that I need, right? Like, that's the cool thing. So I'm really wanting to try to make this number become a 0. So I'm working in base 3, and what I would need to add to that 1 to get it to be a 3 would be a 2. So it'd be a 2 in the 3's column, so it'd be 2, 0 that I'm adding. But if I add 2, 0 to the second number, I have to add 2, 0 to the first number. So I end up getting on the first one, 1, 0, 2, 2. And on the second one, I get actually 2, 0, 0, right? Because 2, 0 plus 1, 0 would be kind of like 3, 0, but there's no 3 in base 3, so it rounds the next value up. And then now I've got the problem, of course, with subtraction right here. So I want to add a number to the 2 here so that it will become a 0. So I do that by adding the number 1, 0, 0. On this one, this becomes 1, 1, 2, 2. And the bottom actually goes up to 1, 0, 0, 0. So the subtraction, lovely as it is 1, 2, 2, base 3. All right, to finish up this lesson, we're going to take a look at some mental mathematics. And again, remember, mental mathematics is not approximations. We're just trying to talk about what we can do in our head to do a problem more quickly, more simply. The first mental math one is called breaking up and bridging, and we've seen this one before. We take the second number and we break it apart, so 30 and 8, and then we do the subtraction, so we have 46 minus 30. Actually, I'm going to write it like this. Well, that's okay. So 46 minus 30 is 16. And then we subtract off the 8. So 16 minus 8 would give me the 8.
Do you want this open or shut?
All right, our next example is called trading off. It's really just equal additions. It's really what it is, but we can do it pretty nicely and pretty quickly. So kind of one of those things that has multiple names. So you'll notice that you're adding 2 here, and the trade-off is to add 2 here. So you end up getting 48, and sorry, I should have done it like this. That's better. And this one becomes 40, and so the subtraction is really nice. 48 minus 40 would be 8. So it's a trade-off. And then the last one's called drop the zeros, and the idea of drop the zeros is simply to ignore the fact that there are zeros here and to just focus on the numbers that are non-zero at the beginning. So I have 46 minus 34, which would be 12. So that means that my answer with the zeros would be 1200.